Hello students, welcome to this lecture number 3 on thermodynamics. In this lecture, we will be discuss a very important part in the thermodynamics chapter, that is the expression of the work at different conditions. Because we are dealing with the energy, and work is one of the forms of the energy. So we will discuss the expressions, different type of expression in work at different conditions. So today's heading of this video will be expression of the work. Expression of work at different conditions. Work at different conditions. Many chemical reactions you can observe that they are accompanied with the generation of the gas, and as well as there is a generation of the heat, and this generated gas is capable of doing some mechanical work. We have to quantify these changes and relate to it to the internal energy changes of the system. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. So we are going to deduce the work done by a system, and first we have to see which type of work a system can able to do, and we will be concentrated on the mechanical work, and this is also called the PV work, pressure volume work. So we will deduce, we will make a expression of the two types of process work done by the gaseous system, that is irreversible process and other is reversible process. First let us understand what is reversible process. Reversible process is that process which is carried out in such a way that at any time of this process you can able to reverse this process by an infinitesimal changes, and this process is very slow, and every time this process is going on you will find that one thing, it will be in the equilibrium with the surroundings. So this process is very slow, and this is called the reversible process. Any other process other than the reversible process is irreversible process. So you understand what is reversible process? Reversible process is there is a changes of infinitesimal amount of the pressure or the volume, that we will discuss in detail when we go to the reversible work done by the gaseous system. To understand the gaseous system which is going to do the irreversible work, for that we have to take one cylinder. This is the system that we are taking. This is a cylinder, and this cylinder is having 1 mole of ideal gas, and its total volume, initial volume of this gas is V1, and internal pressure of this gas is P, and we are going to deduce the work done by this gaseous system, where you have observed a piston is here. This is a piston, frictionless piston. This piston will go up and inward and outward direction. This is a frictionless piston, and when this piston is going from the initial volume V1 to the final volume V2, this is the final position of this piston, and the gas is P, and the external pressure of the gas is Pxt. We have to understand, we have to deduce the expression that work done. You can say this work done is we call the irreversible work done. Irreversible. This is irreversible work done, and we have to find out the relationship here. You can that we have first the cross section. Let us understand the cross section of the piston cylinder is A, and we have to work out the when there is a expanding of the gas from the initial volume V1 to the final volume V2 as against a constant external pressure, that is PXT, constant external pressure, and as it is a constant. So what we have to do? We have to do the operation in a single step. That is from V1 to V2 we have to change this in a single step. That is why it is a very, very fast step. We will call it is a irreversible process. And this irreversible process, we observe what we have to deduce the work done by this irreversible process. First, we have to understand the change of the volume. What is the change of the volume in this case? When there is a expansion of the gas from the V1 initial volume to the final volume V2, and it will give a change in the volume. We can write it the change of volume. Change of volume is equal to, we know when the area of cross section is A, then A into L. L is the distance covered by this piston. Distance covered by this piston is L. So we will get A into L, and that is naturally the V2 minus V1, and we will put is delta V. The change of volume is delta V. Now we have to deduce the work done. Work done by the piston when it is expanding. Work done, we know, that is force into the displacement. Force into the displacement, that is the mechanical work. So how we get force? Force, we know, basically the pressure divided by the area of cross section. It is A. Pressure is given here, P external pressure, and area of cross section is A. So, sorry, that is I have done that different thing. That is not the case. Force pressure equal to force divided by A. So this is pressure equal to force by A. So we can get the pressure, force equal to, from this we can get the force, that is pressure into A. Now we put this value here, work done. This is the work done, that is work done reversible is equal to, given by the force is equal to Pxt into A into L. L is the distance covered by this piston. So displacement, that is L, and the force is this, and we have to put a minus sign here because this is the convention. When the work done by the system, then we will call it is a minus work. We call we have to put a minus sign here. But when some work has been done on the system, suppose it is a compressing, we are compressing the gas, at that time the work done will be plus. That when we do the work on the system, it will be plus. When the system itself doing the work, then it will be minus. So here we will put this minus, and A into L that we are already observed, that is a change in the volume. So we can write this equation external pressure, and that is given by minus sign, into delta V, that is the external irreversible pressure has been irreversible work done by this gaseous system when it is expanding from V1 to V2. Okay, so this is the expression work we have done, that is work done irreversible. Work done irreversible, and we have understand what is reversible and irreversible things. Okay, now another type of work, that is when the external pressure is not constant. Here external pressure is constant. That is why at a single step we have to do this action by expanding. We are expanding this volume V1 to V2 in a single step. But when the external pressure is not constant, at that time what will be the work done? And this type of work done we will calculate, that will be the reversible work. What is reversible work? And one thing that we are forgot to tell you, that is here you can see the graphical representation of pressure and volume, and you can see that is this A into, this is the area. This area will give you the work done by the system. Understand? The irreversible work done by the system. And now we are going to understand the reversible work done. At that time what will happen? Suppose we are changing the work done, changing the pressure in a very infinitesimal amount, means very minute amount. At that time this graph will be like this. So we are discussing the expanding, that is this is the pressure and this is the volume. So when this is expanding means we are changing the pressure by an infinitesimal amount, means the pressure is gradually being changing with some, by decreasing it in infinitesimal amount, and at that time this curve we can see that is looks like this, and the volume, that is V1 to V2, and here pressure is coming from the P1 to, that is P1 the initial pressure and P2 is the final pressure, and that should be given by this curve. This curve is basically, you will see the work done at the reversible work done. This is work done reversible. So this is work done reversible. So how do you able to calculate this work done reversible? That will be calculated by when it is expanding. At that time we can write work done reversible. Work done reversible is minus, and you have to give a minus point, and we have already discussed why it is so, because when the system itself is doing the work, we will say that work done will be minus. When we are doing some work to the system, it will be plus. So we can calculate the work done, reversible work done, by this way, with where the volume is changing from V1 to V2, and here external pressure is this, and the daily change in the volume dV. So external pressure is changing. In case of it is expanding, means external pressure will decreasing infinitesimally, and the internal pressure is higher here. because it is expanding. So at that time the work done we can do by this. So we can do the work done with this effect, with this from this formula, the V1 to V2 in the Pxt into dV. Here one thing that we have to understand, we now want to express this pressure term in terms of the internal pressure, means the pressure of the gas. So this term we can write this V1 to V2 P internal minus dP. External pressure will be lower by infinitesimal amount than the internal pressure, then we will see the expansion work. But when it is a compression, it will be different, it will be plus. So we will put this dV and we will get, how we will get, let us understand. So this is the, we are integrated the work done. This is the integrated formula of reversible, W reversible, that is with minus, and we get from this here P internal minus dP into dV. So we can write this. Here you can see V1 to V2 P internal into dV minus V1 to V2 dP into dV. See, dP into dV is a very small quantity, so we can neglect it. So after neglecting, we will get this value V1 to V2 P. We are now assuming that P internal means P. So you will get this. So we can write again V1 V2, that is RT. Suppose n mole of gas, this is the ideal gas, and for this we convert the P in terms of your universal gas constant, Pv is equal to nRT, and Pv nRT divided by, you will get the V, and it will be this. And when you integrate it, it will come in minus nRT natural log V2 by V1. So we can further write this nRT 2.303 log of V2 by V1. Also we can write in this term in terms of pressure also 2.303 log of P1 by P2. This is the two terms, the very important term that we can understand. Okay. So what is the two equations that the expression for the different conditions? One reversible and another is irreversible. For the reversible, that the formula will be minus nRT 2.30 log V2 by V1. When it is this work done by the system, then it will be minus. Work done by the system, then minus, but work on the system, then this you have to tell plus. So we will get this very important formula. From this you have to many numericals will come and you have to use this formula. Okay. So this is how we can able to know, we can know the expression of the work done at different conditions. Different conditions means one is irreversible work and other is reversible work. This is a irreversible work done and the reversible work done and the irreversible work done, that is already we have done. That irreversible, that is minus Pxt into V2 minus V1. Let us understand the free expansion. Free expansion. What is mean by free expansion? And at that time, what will be the work done? In the free expansion means we are expanding the gas in the vacuum. So when we expanding the gas in the vacuum, then P external will be 0. So W will be 0. So when there is a free expansion, the P external will be 0, that is why W will be 0. And the first law of thermodynamics can be written in different ways that we can see now. What is the first law of thermodynamics? That is the mathematical expression that we know. Del U is equal to Q plus W. So we can write this equation further, Q minus P into del V. Suppose there is a process, first process, that is a constant volume. Constant volume process means del V is equal to 0. At that time we can see that del U is equal to Q. Means that is a very, very important thing to understand, that when there is a process which is at the constant volume, at that time heat absorbed by the system will be equal to its change of the internal energy. So this is a very, very important to understand. Okay, so we understand the free expansion, then we understand at the constant volume what will be the internal energy change. That we have initially we have initially we discussed that we have to interrelate all this quantity, that is work done and that is the heat, with the internal energy change. That you can see when it is constant volume process, the internal energy change will be equal to the heat absorbed by the system. Now we will understand another thing, that is the isothermal process. What is isothermal process? Isothermal process, it may be reversible or irreversible. Or reversible process. It may be reversible or irreversible. Okay. For this isothermal process, we have to see, we can express the first law of thermodynamics in different way. First, we understand what is isothermal. Isothermal basically when delta T is 0, means the process is being carried out at the constant temperature. So at that time, Joule has experimental proof that at that time what is going to happen, the del U is equal to 0. So first law of thermodynamics is this. So we can write 0 plus Q plus W. So we can write this Q is equal to minus W. Number 1, first, for irreversible isothermal work done. At that time, irreversible work done we have already calculated, that will be Q is equal to minus P external into delta V. That is the external work done. Irreversible Q is equal to reversible work done. Q is equal to, in this case, the work done that will be different, 2.303 in RT into log of V2 by V1. For another type, adiabatic work, why we observe? At that time, adiabatic work, the work done, because Q equal to 0, adiabatic work with Q equal to 0. So we can apply this formula and we can found that internal energy change U is equal to W adiabatic. So this relationship that you have to always keep in mind, because there is a lot of questions will come from this conception, right? So we already understand what is expression of the work at different conditions, and how the first law of thermodynamics can be expressed in different ways. Now we will do some numericals that will give you much more clarity on that concept. Okay. A gas absorbs 250 joule heat and expand from 1 liter to 10 liter at the constant temperature against external pressure of 0.5 atmosphere. The values of QW and increase QW and the internal energy change that you have to calculate. When this type of numerical comes, first you have to understand which type of process it is. When it is say against the external pressure of 0.5, means it is a reversible or irreversible. That you have to first understand. This will be the irreversible process. And for this irreversible process, what will be the work done? Work done is W is equal to, it is expanding. So the work is done by the system. So we can write minus external pressure into V2 minus V1. External pressure is 0.5 and V2 minus V1 is equal to 9. So it will be coming around 4.5 liter atmosphere. See, here what the answer, you have to answer in terms of joule, but it is given by liter atmosphere. So for that we have to convert it into the joule. We know 1 liter atmosphere is equal to 101 joule. So if we can convert it, it will coming around 455 joule, and that is minus. So now we apply the first law of thermodynamics. First law of thermodynamics is del U is equal to Q. Here expansion work is done, minus W. So Q is equal to, Q is 250 and it is 455. So we can calculate and it will coming around minus 205 joule. So you can see that when there is a expansion work irreversible, at that time internal energy is lost. There is a internal energy minus, means that system lose some internal energy, and how much internal energy lost? That is 205. So this will be the answer. 250 is the heat Q. W we are already calculate minus 450 joule, and the internal energy will pass. Okay, this is the answer, and that is all for today's lecture. Hope you enjoy this lecture, and if you understand and if you enjoy this lecture, you can share with your friends. Thank you very much for watching, and the next lecture we will understand another very important thing, that is enthalpy. Then all the best and be best.